afternoon. It is so nice being here and meeting all the old friends. And I'll be talking about the landmark in this area, balloons, astronomy, balloons and satellites, basically space astronomy. And this job is a bit simple because the landmark in space astronomy in TIFR is AstroSat. We all know about AstroSat. And as Mayank was asking me to reduce so that we have lunch in time, so I will make it fast and tell why AstroSat is the landmark and how we achieved that. And while doing so, my approach will be completely personal and anecdotal rather than going to the rigorous of that what cost all of us to work on this very wonderful instrument, how we went about doing that. So there may be, I may be biased in picking up some names and ignoring some names. I ask for apologies in advance. Basically, space astronomy, I think I should introduce with some pedagogical picture. So astronomy is nothing but studying about the cosmos, studying about the stars. So in this picture, what we show is that we use the all branches of electromagnetic radiation to look at the cosmos. And this all the way from radio, infrared, optical, X-ray, gamma rays, and sometimes we do use non-EM signals also, like neutrinos or particles, even cosmic rays. Okay. Now the thing is, what is shown here is that most of this electromagnetic radiation is absorbed by Earth's atmosphere. We don't see them here. We have to take the instrument up above the surface, at least to have some chance of looking at them. What is plotted in the half length, how high you need to go above the Earth's surface in kilometers so that these wavelengths, at least 50% of the flux come to the top of the atmosphere is visible. So you can see that only windows are radio and narrow optical beam, optical range. So in that sense, optical astronomy has huge advantage last 300 years, and the space astronomy is only recent, last 40, 50 years. And in fact, from the optical observation, we know quite a lot about cosmos. We know almost everything. In fact, if you can, there's some in the late, in 20th century, every single known laws of physics are applied up there in the skies, and every theory is proved to be operational there. So there is like argument and arrogance saying that, like Arvind said, give me a lever long enough and I'll move the Earth. Similarly, Eddington said that even if there is a civilization which is covered by dust, we can't see outside, give them laws of physics, they can figure out there are stars, and we can calculate by simple pen and paper what is their mass, size, and temperature of stars. Okay. Now, when I say that every single principle that we physicists discover in the Earth is applicable there, is simultaneously a profound and a trivial statement. Profound in the sense that this tiny Earth, what we discover in the laboratory, is applicable throughout the universe. And trivial in the sense, if it is not applicable, we won't know it. We won't realize it. We won't accept it. Okay. Now, what I want to emphasize here in the space session is that there exist objects in the universe which copiously emit in non-optical region, like the strange animals called gamma ray bursts, which emit in a matter of seconds, equivalent of the rest mass of the whole sun. And now we have some idea that coming during the birth or death of compact objects, but exactly how we generate, we don't know. Similarly, blazars, which from the end of the universe, beaming towards us. So there are so many mysteries in this one. So space astronomy is important. That is the context I want to put in this one. Now, there is a fascinating story of space astronomy, how it is developed from Second World War onwards. Because to measure this radiation, which cannot come up there, you have to take the instrument above, either balloons, rockets, or satellites. So initially, there is a captured German V2 rockets, which were used to send instrument, measure. They are very, very low sensitive instrument. They did measure X-rays coming from sun. And as I said earlier, all physics of stars we know. And from our knowledge of physics of stars, it's unlikely that the then instruments will detect anything from stars, because sun emits very, very feeble X-rays, one part in 10 million of the whatever it emits in optical. So general consensus, there's nowhere else to be seen. Okay. Then these are from rocket, which can observe stars only for a few seconds. Then 57 to the first Sputnik was launched. It's a great space race. And 62, first non-cell X-ray source was detected at the birth of X-ray astronomy. So the detection of something so bright is contrary to whatever we expected from the traditional classical physics. After that, the space astronomy zoomed up. So the first X-ray source detected is Cygnus X1, and it is known to be a black hole sources, because the black holes, till then we had only concept from the radio observation. The first confirmation of there exist some objects which is massive than any ordinary stars, and this is nothing we know about this one. So many of the space astronomy observation, in particular X-ray astronomy, is about such compact objects. Now, where are we in TIFR? I want to segregate the period in 3 periods, which is completely subjective. Okay, the first is what I call 67 to 80, the era of dreamers. Okay, so when the first X-ray source was detected in 62, there is fascinating development happening in MIT and American Science and Engineering, a private institute funded by Riccardo Giacconi, who got Nobel Prize in 2002. B.V. Srikandan was witnessing all this development right then and there, and he came back and initiated in TIFR. So there is when I joined in 77, this issue was full of excitement of this new area of X-ray astronomy, and I want to share a little bit of the excitement because I was towards the end of it. And 80 to 2000, I'll call era of strugglers. I'll come to that wide way, say that. And 2000 onwards, when we proposed AstroSat in this one, let's say new Renaissance era, and we could make competitive observation in space astronomy. And Nabha Mandal gave a list of pioneers in X-ray astronomy, and he selected 3 for his thing. From that same list, I'm selecting 3 who have done pioneering work in space astronomy in TIFR. Of course, B.V. Srikandan, as I said, he was witnessing the birth and growth of X-ray astronomy. He was fascinated by it. Immediately come and say that, of course, we had this well-developed balloon infrastructure, mainly for cosmic rays. It was straightforward and almost trivial to convert it to a platform for X-ray observations. And he motivated the band of youngsters to do the X-ray astronomy in this one. And of course, if you take a lenient view that space astronomy can be done not only by electromagnetic radiation, but also particles. So Kumar Biswas, I mean, when we are in the students, it was fascinating that there is Kumar Biswas. He proposed something for a space lab, got accepted, and something made from India will go in space lab and fly and measure the cosmic rays and measure the composition anomalous cosmic rays. In that sense, there is a pioneering work by Kumar Biswas. Of course, Professor Daniel was a very well-known cosmic ray physicist, but he is the person initially handled the balloon facility, and later on he was instrumental leading the infrared group, part of the space astronomy in TIFR. Now, as soon as this one initial days from 62, let's say almost 75 or 77, most of the observations are done by rockets and balloons. And since in TIFR, we could quickly convert our know-how to make the X-ray measurements, we were highly competitive. Looking at the Cygnus X1, I'll come back again and again to this source, first black hole source, and how rapid changes are seen, okay, and some other source, this one. So any measurement in that is fantastic observation, and we had enough technical expertise, enough enthusiasm, enough youngsters who are dreaming and dreaming big and doing this one wonderful work in that. Now, out of this many things, I want to subjectively pick out these two gentlemen. There are many people contributed, but there are two reasons I want to highlight these two gentlemen. One, they are very strong personal influence on me. Second, they are the prime motivating and force for realizing Astrocyte. Professor Prahlad Agrawal, my thesis guide, of course, he taught me everything about the building X-ray detectors. But I'm mostly talking about the other style of learning which I did with this student. So he was part of a satellite experiment called HEVO-1 and building proportional counters at Caltech. When he came back to India, he brought the technology and he was using it multiple projects in India. So one of the most fascinating thing in Professor Agrawal is that nothing is impossible for him. In the sense, suppose we say that this won't work, he will always bang his table and say, why not? Okay, so that why not culture in the group is mainly motivated by Professor Agrawal. So here, one of the large area X-ray proportional counter which he built and operated, and this is the forerunner for the one of the biggest instruments in AstroSat. And one more thing, he is extremely practical man. Without his practicality and his political sensitivity, it would have been impossible to maneuver and move such a huge project like AstroSat through various national organizations and ISRO culture. And Professor Shyam Tandon is a completely contrast in nature, in the sense that he's the one person during those days, everything was built from first principle, and there were some style of doing things very fast and quickly. He's the one, he imposed quality in each and every one what is being done. So this quality consciousness is many of us learned painfully later on with our close interaction with the ISRO culture and ISRO way of doing things. From first principle, he has imbibed from beginning itself. And other things which is extremely fascinating about him is that from every single problem, maybe technical, maybe physics, maybe philosophy, he has the ability to look at it and understand it from first principle and quickly change and look at it from any differing perspective. And he is one of the person responsible for the infrared telescope. Actually, it's a technology marvel. I remember in the 80s, Baji covering this and putting in the front page of Frontline and saying that what a wonderful instrument it is. That I'll come to this. These are the two other people who contributed to the AstroSat. Now, at that time, there were multiple ambitious projects. Okay, so we are doing extremely competitive research as compared anywhere in the world. Like, for example, as I explained, Professor Agrawal was doing the largest hard X-ray telescope, and Shyam Tandon was the largest far infrared telescope. And there is a University of Calgary collaboration for hard X-ray astronomy. And Professor Damle at that time also realized that you need huge collaboration, and he had a vibrant collaboration with the Soviet people for a Natalia Gamma ray experiment. And as I explained, there will be space lab experiment. And in the west, things were moving on from balloons and rockets to satellites. Okay, so the Indian rocket and satellite industry is in a nascent stage. As early as 1975, Soviet Union gave an opportunity to launch the Indian satellite. That was basically an experience for Indian people to build satellites. And in that thing, the neutron monitor TIFR collaborated the first satellite. And later on, the Bhaskara, which is a basically remote sensing satellite, there was a off-sky X-ray monitor. Professor Agrawal was developing that. I still remember I joined in 77, in 78 or 79. It was launched, it must be 78. Professor Agarwal is in Goddard Space Flight Center in US, and its propulsion counter is leaking. As a student, I had to carry this propulsion counter all the way to the airport, Centaur Hotel, where you are now sitting, a handover, he take to US, test for leak and bring it back. So such things were happening at that time. And of course, Professor Agarwal also was instrumental in making a rocket experiment for soft X-rays, which was one of the first all-sky very low energy map, which eventually formed the thesis of Professor KP. With all this excitement, 1980, I call it era of struggling started. Why do I say that? Actually, this date could be 1985, because that far infrared telescope Spain Shamdenton built initially 30 centimeter, then 75 centimeter. Unfortunately, 1980, it went to the sea because we couldn't recover it. He rebuilt it, T100, 85, and beautiful results were coming by late 80s. And the Anuradha experiment they talked about, Kumar Biswas was responsible for Space Lab. The results launched in 85. Though these results will keep coming post 80, personally, I feel that 80 is the time is something changed. Basically speaking, space astronomy moved on to the era of satellite. Two reasons. Okay. One is that in balloons and rockets, observation time is very small. Now we can continuously observe many sources. And secondly, there were many new technical improvements quickly came, which was imbibed in a satellite. We could not do it in the rockets and balloons. Like 77, first major X-ray satellite, UO1, and Einstein Observatory 1978, which using the X-ray focusing. So I'll briefly tell this focusing, non-focusing part in X-ray observations. So X-rays come, you put a detector, you detect that. Okay. Now, if you want to increase sensitivity, you need to focus X-ray single point, and reflecting X-rays extremely difficult. They are very short wavelength, they will scatter rather than reflect. You need a grazing incident. So the making a very highly polished grazing incident scope is a technical marvel, which has happened later on in Chandra Observatory. Okay. So that technique, this is years of development in the West, and we didn't have any headway in that. So I remember in the late 70s or 80s, we go to the library, suddenly there is a full volume of astrophysical journal letters telling the latest results about one satellite, like IRAS or HUO1. So there, the results were totally outstanding and nothing what we have observed and experiment. And I still remember in 19, there is a one huge NASA memorandum of X-ray astronomy 80s. Me and KP in the night, after dinner, we'll go and look chapter by chapter. So initially, our heady days, we have learned all about neutron stars, black holes, etc. But what the improvement sensitivity of the focusing detectors in satellite platform did was that detecting X-rays in all types of various sources unimaginable, starting from normal stars, supernova remnants, clusters of galaxies, active galactic nuclei, and even ordinary galaxies. So looking at that, our own effort looked very trivial, and something hit me and KP. And KP much more later on confessed to me that at that moment he decided that in India, somehow he will bring X-ray focus indeed. And he did indeed for AstroSat. So what were we doing? Okay. So there were many things. For example, Shyam Tandon moved on to fifth force experiment, later on moved on to Ayuka. But the IR telescope continued with the balloon observation by putting better focal plane instruments, and IR group moved on to a lot of ground-based optical observations and optical physics. And Professor Agarwal continued with the large X-ray proportional counter and making multiple X-ray data. Professor Manchanda went on doing different types of X-ray detectors, and he did the ground support for HLA satellite. And Professor Damle continued the Soviet collaboration. So the smart young man is, you may be recognizing there on the right top. And one more thing happened at that time is proposal-based archival data analysis. So generally doing science, you need to have the hands-on experience of using data. That the era, most of the data were public, and Professor K.P. Singh pioneered that effort in India. I remember we did a sort of thought experiment, me, Wahi, and KP. KP led this thing in a matter of, it's a project mode. We started a paper factory sort of. In a year and a half, we had dozen publications. So when we wrote a proposal, data is to come in magnetic tapes by surface mail, and we used to drag it and do all this work. These are all important for later on. I'll come to that soon. Now, Professor Agarwal, the never say die spirit, in this spirit also, he was needling ISRO, saying that X-ray moved on. We can't survive in this area unless we have satellite platform. Of course, Indian rocket system was not matured. It is till 2000. Okay, so whenever this opportunity comes, he grabbed it. Okay, for example, there is Polar Satellite Launch Vehicle. They were experimenting development flight 1, development flight 2, development flight 3. In development flight 3, there is some opportunity of putting a small propulsion counter. Okay. So this was a quick effort saying that we are testing the rocket. If you want, you make this instrument. Of course, we are building propulsion counters for balloons, etc. Balloons is little bit easy. When you send it up, it doesn't work, bring it back, repair it, and send it again. But we have to build something which will last for years together. There's a order of magnitude higher planning involved. I still remember the ISRO, some team came to inspect whether we'll quickly deliver, because they are testing the rocket within a time from 1 year. You have to do that. And evening we are testing the detector, we're leaking. I remember why we are going out and say that, come on, one last effort. Finally, we demonstrated, and this was sent in space. More than that, it was first experiment. So basically, it's a photometry. It detects how many X-rays we detect from the sky. But all that we learned from KP Singh came useful. So whatever data is available, there's a huge number of publications. You can notice many of them. Dr. Kasturangan was graceful to be a co-author to the newspapers, and it infused a large number of students, and large workshops and courses, and wider available data was norm in X-ray astronomy. So time was ripe to move on to next phase, to have our own full-fledged international observatory. That is the Renaissance AstroSat. Now, AstroSat, now we have to pause, and I have to explain a bit. As I explained, rocket technology goes zooming up in the West. Not only these satellites, which I explained, NASA had the 4 great observatories. Each of the wavelength, there is the best possible satellite, like gamma rays, Compton gamma ray observatory, Hubble Space Telescope, Chandra X-ray Observatory, and space that. So all wavelengths are fully covered. So right now we are beginning. Do we go back to the 1970s and 80s, have the same small X-ray instruments, or do we think of something there? The philosophy is simple. There are certain things which you are expert in, build on it. Certain things, but don't forget the science. And what new science we can bring into that. So generally, when the space era had come, now every object emits almost in all wavelengths. So if you want to apply your physics, it's very good to have multi-wavelength observation. These days, this has become a trend or a fashion. So maybe, okay, our individual instrument may not be comparable to the great observatory of each wavelength, but they're sensitive enough for the bright sources to make measurement all the way to infrared to gamma rays. So with this concept, it is a doable, and also it is competitive and scientifically rewarding. So it is the first multi-wavelength astronomy satellite launched at on the 20th of April 2015, and large number of institute, university, everybody worked together. Now here, again, I will explain each of the instrument here itself to get the legacy of what formed during the early days and the struggle years, so that we can move forward. Let's start with ultraviolet imaging telescope. So there are 5 major instruments. 3 of them were led by TIFR. Other 2 though there is no direct connection, there is indirect connection. So UV telescope is led by TIFR Alumni, Shamtandar. And of course, some critical elements by the leadership of Swarna Ghosh, it was tested and qualified here. And the whole approach of doing the quality instrumentation of Shamtandar, which is started with the balloon experiment, moved on later on for the fourth experiment, and later on in Ayuka, that all came into force. So he single-handedly, single-mindedly moved various organisms of ISRO to make one of the most beautiful infrared telescopes. Why is it competitive? Because it's wide field and very good seeing. So the things, suppose like for recently, the couple of nature papers came on that, looking at the deeply wide field areas of near the galaxies. Okay, so the complete quality conscience and building good telescope came into picture in the ultraviolet imaging telescopes. Then you have the large area proportional counter, PC Agarwal, proportional counter Agarwal. I mean, so he had the experience of almost a lifetime to building that. And this large area proportional counter in high energy X-rays is one of the largest area ever flown. So we had the legacy for that, but building 3 of them and such a large thing in a quick time was extremely difficult. Many people contributed. Of course, Professor Ante also became part of this team. So Ashwat attracted not only all of us, including theoreticians like Ante. So then soft X-ray telescope is the dream of KP Singh. I mean, during the 80s itself, he has said that he will somehow bring the technique or the method of X-ray focusing in India. That is a complete effort from him. And this all-sky monitor was completely built from the ISRO team. But TIFR connection is that identical unit in the collaboration TIFR in 1995, we had flown in Indian X-ray astronomy experiment as X-ray sky monitor. So the legacy or the know-how, there is a hand in TIFR even building this instrument. And cadmium zinc telluride experiment, I think in the days when we are struggling, for example, we are in TIFR and Upendra Desai from NASA came. We say that, what are you doing? He said, we are building proportional counter. Come on, there is a new generation cadmium zinc telluride detector. So he'll, from his pocket, will say this small detector. So me and Vaya will go and fiddle around this one. That experience helped to build this CZT detector. Not only that, I think the renaissance is slightly different. We are better off monetary-wise. I remember in 80s and Professor Agarwal got optical CCD. It was not working and it was lying in the lab for 5 to 10 years. Similarly, X-ray, the CZT detector we bought from Israel. And of course, the first time when we bought in the laboratory, it was not working. So, but we had, Agarwal had this thing, he pushed and this thing and got enough money for me and Vahia went to Israel and find out how to make it work and brought it back. So this is some sort of piggyback experiment in the sense that bringing the new generation X-ray detectors for Indian platform. So this is the details of the telescope, this one, okay, and this is the largest area detector, and this is the each of the conical foils, 40 cells, 130 of them. So this one, each one of them KP painstakingly built. Of course, we were doing there's extreme space crunch in our laboratory when 3 major instruments are being built, and he had to snatch space from the basement and get people to work on it, and foil by foil, we had assembled this one. Of course, X-ray CCDs were collaboration with the University of Leicester. And even now, in the CCD, this one of the finest energy resolution, 145 EV for 6 kV X-rays. And CZT data, which I talked about, based on the CZT detector bought from Orbitic Solution, assembled to, let's say, large area, and scanning sky monitor, which developed from ISRO based on the legacy of collaboration between TIFR and ISRO. Of course, ultraviolet imaging telescope, 2 of them, and Shamtandar is the major responsible for developing that one. So, as I mentioned, this Astra study wouldn't have possible without the active collaboration of the vast number of institutes all across India. And making them working together was a tough job, but eventually, I think there are two major components that instrument building capacity started in the early 70s and even 80s. Some of us took the kept on the flag flying. That helped us, and of course, I should emphasize the complete technical know-how and professionalism and quality consciousness of ISRO played an extremely major part. So this is one of happy union of care for technical competence and professional ISRO and everything coming together and building something very nice and beautiful. So there are certain good things about AstroSat which actually can make it extremely competitive. It is making it extremely competitive. It's in the low inclination for X-ray astronomy. It's fantastic for reducing the background. And we have continuous time tag data. So like, for example, we can, timing is so good, we can connect the timing from launch till today. So even the faintest millisecond pulsar, we can co-add and measure. So with the time base of 7 years, you can go down to extremely faint millisecond pulsar. So this extremely good timing measurements are one of the very good features of this one. And soft X-ray telescope is not that sharp. That actually is a blessing in disguise, because many of the very good focusing telescopes focus the X-rays to a single point. If you look at the bright sources, they burn the CCD or burn the X-ray detector. So since the focal length constraint, frequently lower, the seeing is wider. So even the bright sources without piling up. So this is fantastic for the making X-ray spectrum of very bright black hole sources or transient sources. And we have above hard X-ray polarization capability of the TA major, which was serendipitously much later after design of the detector, which was realized and proven. And now we associate working for the last 7 years. And 7 years, we had a feel-good meeting at ISRO. And I'm now just flashing few of the slides made by Girish during that meeting. So there are extremely good research, I think, so from each of the instruments, and large number of publications. And it's a peak in the publication because we had a 5th year celebration in our own journal, some large number of papers. And AstroSat users all spread all through India, because the spreading the community was important for to get the proposal like AstroSat to be approved. So here in the 80s and 90s, the large number of workshops and schools which Professor Agarwal is instrumental, that proved very useful. So right now we have AstroSat users from universities all across India. And it's a proposed, mainly I think Bombay, Bangalore connection is stronger, I think. So of course, it's open for international collaboration. So right now, AstroSat users are in many international countries. And as I said, publications are decent, around 20-30 every year. So I will conclude here to honor the 115 lunchtime of Vaya. So AstroSat, we took a extremely innovative approach. And based on AstroSat, now there is many offshoot experiments being thought about in various stages of approval. The cadmium zinc telluride instrument, which has been used, similar detectors are proposed for a thing which is jointly with TIFR called Daksha. And infrared instrument is in the proposal stage from TIFR. And based on UVIT, the infrared spectral and imaging are proposed from IAA. And actually, AstroSat helped to understand the technology gap. So technology gap is no longer a constraint in space astronomy. Why? See, previously, for example, most of the technology used are device-based. Okay, many of the devices are denied to us for technology transfer way. But today, most of the technology is software driven. So, like for example, you may not get the highest end FPGA possible. Okay, but even the few 5-year-old FPGA with a experienced person sitting in this row who has experience programming FPGA for various satellites, if you use his expertise, the final product is as competitive and as good as elsewhere. So now technology is mostly software driven and not the device driven. Except, of course, some few detectors, some extremely sensitive infrared detector may be still too difficult to get. And for example, suppose you want to build another astrosat, etc. I personally feel money, etc., is not a constraint. In the sense, suppose you said you want to, there is no technology gap, you want to build something $1 billion satellite for something niche area. So in India, getting $1 billion is less difficult compared to get 100 people who are qualified and willing to work together for 10 years together. Now, if you want a $100 million equivalent thing, you have to make 10 people work together. So having a large number of people, interested people, devoted working together, that culture we are yet to do, I think is in the line. Okay. So with this, I'll conclude and give me enough time for that. Thank you very much.